Okay, are there any questions on the last lecture? So I'll review the last lecture and I'll remind me at the end of this lecture to I have a poll. I want to ask you guys for something. Remind me of that. Okay, so today we're gonna talk about gauge redundancies. As usual, start with a review of the previous lecture. Now, I finally decided that there will be 2 slides called lecture 12 prime on exact-org, 3 slides actually. So I'm gonna cut this down so that we can get to more material. All right, so what did we talk about last time? We talked about nonlinear sigma model. So what was the story? The story is that we've constructed interacting quantum field theories in dimensions less than 3 plus 1. In search of quantum field theories in D equal in 3 plus 1, we are going to go back to classical field theory and learn about another class of theories that we have not really considered. So these are theories. So this is the start of a new section of the course. It's called non-local observables, and we're going to go back to classical field theory. All right. This is the part that I usually include in Q51. So today is the first lecture of that. It will be on gauge redundancies. But let's go back to let's start with the review of the previous lecture. The interacting QFTs that we found was lambda phi 4, or the ON version of that. In dimensions 4, space-time 4 and above, it doesn't exist. And D equals 3 at large N, we found theories like this using Wilson-Fisher fixed point. And D equal 2 and equal 1, we found interacting theories, but we don't quite know whether at this point they are relevant for fundamental physics. Now, what is nonlinear sigma model? The way I presented it might have been misleading. So I just want to make sure that I get this very clear, send a message across clearly. So in quantum field theory, you have a map from space-time M, a manifold M, to a manifold X. That's called, these are the internal field. This is the internal field manifold that we also call the target space. So this is a picture to have in mind. M is a space-time, some manifold, and then there is some sort of a at each point on the space-time, you the field takes a value somewhere on some internal manifold that I'm drawn as X. So for example, if X is Rn, n-dimensional flat Euclidean space, phi is phi 1 to phi n, and the linear sigma model we worked with looked like this, right? So there was a kinetic term, and then there's a mass term. We also talked about the lambda phi 4 term, but let's not worry about that for now. So that started by realizing that here we just summed over all these fields and they were independent, and that could be interpreted as flat metric on this internal manifold, right? So that's flat metric on the internal manifold, phi squared, phi 4 term, for instance. So this is not in the first line. In nonlinear sigma model, so that is linear sigma model. In nonlinear sigma model, what we do is we say there is some internal manifold and it's not necessarily flat. Maybe it's flat, but we pick a non-trivial metric on it. So now the metric on this manifold depends on the points on the manifold. The points on the manifold are field. So it's GAB of phi, del mu of phi A, del mu of phi B. This is a curved metric in X. Now, and then you could include a potential. But even if you don't include a potential, this term the metric depends on the field, so this already is an interacting theory, right? So you don't need to include a term, and I'll actually explain the story of the term a little bit more. So this is what the nonlinear sigma model is. Good. Any questions? We saw that ON model gives interacting theories only in 0 plus 1, 1 plus 1, and 2 plus 1. So in an attempt to relate these lower dimensional models that were worked out to higher dimensional physics, 3 plus 1 dimensional physics, one attempt is to, so what we're trying to do is that we found lower dimensional theories that made sense. We could try to change interpretation and use that for higher dimensional physics. The alternate interpretation of that you could have for nonlinear sigma model is to say X is space or space-time if it's a Lorentzian manifold. If this is the interpretation you're going with, you have to be, there are things that you need to do. First, the target space now has to become a Lorentzian manifold, right? And then we need to respect all symmetries of the target space because the target space symmetries are now quote-unquote space-time symmetries. Notice that nonlinear sigma model doesn't need such an interpretation. Nonlinear sigma model is just quantum field theory like this, where you've picked a metric here that's non-trivial, right? But you could, if you pick X to be the target space, to be your space-time manifold, to pick it to be Lorentzian, and then you write down Hamilton actions that respect all the symmetries of it, then you could view it as you could have an alternate interpretation for it. We give an example of this in terms of 0 plus 1 dimensional nonlinear sigma model, which it was actually a little bit more involved. It was quantum mechanics or relativistic theory, but it's a little bit more involved. I'll comment on that very briefly, depending on how much time we have. So for instance, if the manifold is just that, if you take the internal manifold to be Minkowski space, I'm not very consistent with my D's. I should probably write D minus 1 comma 1. You know what I mean, right? Actually, let's not change it because I have to change everything on the slide again. So if I pick it to be RD comma 1, then I could try to write down an action like this. This is the kinetic term with the flat metric. This is the Minkowski flat metric, right? So notice that one of the fields has a flipped sign for its kinetic term. That is undesirable. But anyway, now this term, the mass term, is no longer allowed. Why? Because this violates. So these two terms are written down. They respect the Lorentz symmetry of this flat space, Lorentz group. However, they don't respect the translation symmetries, right? This term explicitly violates translation symmetry, so you just drop it. In the linear sigma model, that is the reason that we often focus on this action, right? In spacetimes that are symmetric enough and nice enough, sometimes you could write down potential terms that also preserves all the symmetries of your target space. But we're not going to be discussing those theories here. Just know that most of the time we talked about nonlinear sigma model in this form. So the interactions come through the metric. There could be explicit interactions depending on the model you talk about. Questions? All right. So we explicitly talked about 0 plus 1 dimensional sigma model. This was in this interpretation of viewing the field manifold as space-time. We wanted to model this to model a relativistic free particle. So now indeed RD minus 1 comma 1 or RD comma 1 is my field manifold, my target space, right? So the field takes values X, mu, and T, right? Okay. So you have a field in this. So sorry. Now the quantum field theory is 0 plus 1 dimensional, and your fields are x mu's. So if you label your 0 plus 1 dimensional thing by S, your fields are x mu of S, right? But there is a time in 0 plus 1 dimensions, and then there's a time in target space. They need not be related in a very clear way. You could imagine that when you go in between them, there is, like, so you could say 0 x mu of 0 is here, x mu of 1 is here, x mu of 2 is here. Same word line, you could parameterize it differently. You could say this is 0, this is 1, this is 2, this is 3. The differences between these are some EJ that tells you about these gaps, right? This EJ is actually a local time parameterization in 0 plus 1 dimensions, right? This is a derivative of that. All right, very good. So we talked about this. I'm not going to repeat it. The action that you would like, the desirable action for massive and a relativistic particle is like this, but that doesn't look like a nice kinetic term. The trick we used was that we promoted. Well, we realized that we could write this action in this form, promoting this E of S to a field and then performing a path integral over it. Now, when you do the path integral over it, this is basically a Lagrange multiplier. It will force this action on the saddle point of this, not saddle point, the classical value of it, it collapses to this action. But what you realize is that this theory has you've integrated over this guy, which has the interpretation of metric in 0 plus 1 dimensional auxiliary space, the M, and that's like path integrating over the metric, so it looks like a theory of gravity. There's no gravity, dynamical gravity here. The fact that the theory is independent of parameter S on 0 plus 1 is reparameterization invariant. It led to a zero Hamiltonian, the so-called Hamiltonian constraint, and that is a generic feature in theories of quantum gravity. All right, any questions? This is my quick review here. So if you recall QFT1, very beginning, I talked about how quantum mechanics could be viewed as 0 plus 1 dimensional quantum field theory at the cost of changing pictures, right? You interpret your target space as your space. This is the relativistic version of that. All right. Then we talked about an linear sigma model in D equal 2. And we took as our target space a Euclidean space, Sn minus 1. So this no longer has that interpretation. It's not space-time, right? Could be space. Then here's a Lagrangian you would write. So this is a metric on the sphere, n sphere. Target space n minus 1 sphere. Sorry. Now, because the field takes values on the sphere, it means that if you phi a's, norm of them summed, they should add up to a constant. Here's something important to know. Every time you have such situations in the nonlinear sigma model, well, the field phi is, depending on your dimensionality, might or might not be dimensionful. In this case, what is the dimensionality of the field phi? Is 0, right? So phi squareds add up to a number that you can just normalize to 1 and define normalized fields ket and hat, right? Now they live on a unit sphere. Now, this normalization, to do that, you divide by some constant, and that is g. You put it down here. So your action, you write it as, I'm going to write this down a little more explicitly, as there's some coupling that sits here. This is a dimensionless coupling. Is it clear? Okay. This is something that you do every time you're dealing with, well, right. The way to think about it is super intuitive. You have a theory. Their action is has some relevant terms, has some irrelevant. Has some relevant terms, has a marginal term, classically marginal term, right? Naive dimension counting marginal. So that's it. The coupling of that is dimensionless. So we wanted to keep track of that constant. That was lambda phi 4. Over there was m squared. There was a kinetic term, all of that. So you could view actually as a normal renormalization of the field as the running of the coupling of the kinetic term. That's one way of viewing things. Right?
Can you repeat that?
So this is a kinetic term. Right? Then lambda phi 4. As you run, what happens is that these guys change. What happens is that phi itself changes, so you could view, well, there's actually a renormalized one has a z in front of it, right? Now, you could view this as sort of like the coefficient coupling here changing, right? But we don't do that because we want the kinetic term to be have a standard normalization. So I eat this, renormalize this to 1. That's why we define renormalized fields, and then that pops up here. The z pops up here. All right, but here, your action, there is one piece. You don't have several couplings. You only have one coupling, and the kinetic and the interaction part is all packed together. There's only a single coupling. So that's why you want to write it as a scalar outside, as a constant outside. Right? This is something that we do in QED as well, as a matter of fact. That's why alpha squared is the constant we work with, not E. It's precisely the same reason. I'll do that today, hopefully, if there's time. All right. So, okay, so this is the theory. A good way of dealing with this is to define this is a n vector, right? So take n minus one of these guys to be a bunch of fields, and then the last one is just square root of 1 minus pi squared. This has ON symmetry realized non-linearly. Once you write it in terms of the metric, this is what the Lagrangian looks like. ON minus 1 subgroup of ON is linearized, is realized linearly. However, there's this bit that shows interactions, right? And that's coming from this metric on the sphere. Now, again, I repeat this. It is crucial to realize that this has up to infinite derivative interactions. However, there's the symmetry principle tells you that it's all controlled by single coupling. So this whole thing, even though it has infinite number of derivatives in it, it's only a single direction in the theory space. This theory is nice because of that. These terms in the expansion are locked together due to symmetry, right? The symmetry is large, and that's a lot. That's why. This includes, as I said, an infinite number of interaction terms dictated by the symmetry, but controlled only by one coupling. What we did quickly last time was to look at the Callan-Simanzik for G and the endpoint functions, actually 2-point function of 1-point function of sigma and 2-point function of pi. Here's what the Callan-Simanzik is, and the answer was that we found the beta function and the gamma, which is the field renormalization. Importantly, what we found was that for positive n, for n larger than 2, this theory is asymptotically free. Asymptotically free means that the beta function is negative. Sorry, maybe I should say that. That makes sense, right? Asymptotic means that high energies, then it's free. Think about n equal 2. So what happens at n equal 2? The beta function vanishes. What are the possibilities? It's possible that the theory is actually a CFT, at that point. However, a more likely scenario is that it vanishes only one loop. You have to go to higher orders. This was a one loop calculation. Good. Any questions?
You are not able to know that just from looking at the bill. You know, it's CFD or
no. Just have to do calculations.
I mean, you can do n the calculation to n loops, still you wouldn't be able to.
So you see, exactly. That's why there are non-perturbative methods in quantum field theory. And those non-perturbative methods rely on symmetry. So, yeah. That's a whole different course. I'm happy to teach at some point if the department wants, but we're not doing that here. But indeed, if you do this to arbitrary order in perturbation theory, you haven't established a CFT. There are examples of well, there are examples of theories that nobody knows whether or not they are UV finite, they're sensible, and people have calculated up to like 5 loops or something, and those are absurdly difficult calculations. And up to 5 loops is all finite and good, but nobody knows. There are supergravity theories like that. All right. Now we're going to talk about very briefly about nonlinear sigma model in larger than 2 dimensions. Good? It's clear what it is. And I'm going to tell you about another theory that exists. Very, very briefly. I think I just have a single slide on this. So this is the same nonlinear sigma model on sphere. This is your action, but now you're in higher dimensions. So first thing that you notice is that in D equal 2, this guy was marginal. Now in D larger than 2, this is power counting irrelevant, right? So what you would do is now this coupling dimension full, so you take the dimension out and write it in terms of a dimensionless coupling. Think about Wilson-Fisher. What happened in Wilson-Fisher? In Wilson-Fisher, we had a scalar field that was marginal in 4 dimensions. We did loop calculations. It was irrelevant. So the theory didn't exist. We went below 4 dimension in 4 minus epsilon. We got something nice. Now, what are we dealing with? We are dealing with a theory that in 2 dimensions, the coupling is marginal. Naively marginal. We did the 1 loop calculation for n larger than 2. The theory exists. Now we're getting bold. Maybe we could calculate it in 2 plus epsilon and it will still exist. The operator 2 plus epsilon is irrelevant. But if epsilon is small, maybe things are good. All right? Is that clear? Okay. So you calculate the beta function. I'm just going to pull it out of a hat. This is the calculation, but now you know how to do these kind of calculations. What you find is epsilon over 2, which is not surprising. You should remember, if you recall from Wilson-Fisher, this is the structure of the linear term that you find in beta function when you doing epsilon expansion. Epsilon over 2h minus n minus 2 over 4 pi h cubed. All right. Oh, sorry. Right. There is something sketchy here. No, that's good. No, that's perfectly fine. Yeah. This answer should match this. Yeah. This is n minus 2 minus 1 over 4 pi g cubed, h cubed. Yeah, that's good. There's nothing sketchy here. All right, good. Now, this is the term that we found in 2 dimensions. And the fact that it was negative meant that the theory exists. This is negative. This is positive now, right? What happened in scalar field theory was that in 4 dimensions, this was positive. The theory was bad. We went below 4 dimensions. This was negative, so we found the cancellation. Here, this is positive, so we go above. This is positive. Now we hope for cancellation. It does happen, and it's perturbative if n is large. This is we find a new weak coupling, a new fixed point at this particular value of the coupling at large n. So you find another RG flow that is all within perturbation theory, and you go from the trivial fixed point to a UV to an IR fixed point. This is also a Wilson-Fisher type. Good. They're with me. I'm going to summarize it and tell you, make a comparison. So the lambda phi 4 and below in 4 minus epsilon dimension is now we're comparing it. So this is Wilson-Fisher, that type of Wilson-Fisher. This is nonlinear secant model of Wilson-Fisher in 2 plus epsilon dimensions. The operator is naively irrelevant in 2 plus 1 epsilon. This naively relevant, right? We calculate the beta function here. This is the beta function here. In the scalar field theory, the beta function came out to be positive, so that's bad. As I said, you go below epsilon dimensions. This goes up, this goes down. They cancel. This is the opposite. This goes down, this goes up, and they cancel. You find okay, good. So you find fixed points. Now let's take derivatives of the beta function, right? The derivative of the beta function vanishing tells you you're at the fixed point. What does the second derivative of the beta function telling you? Yeah, is it stable or is it unstable? Which direction are you flowing? Are you flowing towards the infrared, or are you flowing towards the interacting theory, or are you flowing away from the interacting theory? Here's what the beta function looks like here. It goes down and then it comes up, becomes 0 because lambda increases, and here's the IR fixed point. So it's pretty clear that you're flowing from the trivial fixed point toward the Wilson-Fisher. This one is the opposite. So you're flowing away from the fixed point, right? This is the stable one. So this kind of fixed point is less interesting, right? Because you don't expect that if you have, this is the interacting theory sits in the UV, you do RG and you find the trivial theory in the infrared. The direction is the opposite, right? But it is sort of built in a sense, if you think a little bit about it by structure, but construction is a little bit like this. All right, is that fair? Are there any questions? Now there are all sorts of versions of this. Large N is one trick we have in our arsenal. We have another trick we don't have time to talk about in this course, but the principle is symmetry, supersymmetry. If you have supersymmetry, sometimes you could integrate RG flows all the way because the symmetry protected, non-perturbatively. Not even like your first order, just non-perturbatively protected because there's some symmetry that protects it. All right, any questions? Now I have 3 slides about exact RG, and then we move on. It's very convenient that there was a talk about this yesterday, but so what is exact renormalization group? Remember again the Wilsonian RG. What did we do with Wilsonian RG? We put a sharp momentum cutoff. So we said there's a path integral over the field phi. We're just going to cut off. We're only going to pass integrate over momentum modes, Euclidean momenta that are up to a certain k squared, lambda. This is called a sharp momentum cutoff. This, and then when we move the cutoff, we are integrating things out. There is another idea called the smooth cutoff. You're not integrating anything out. What you're doing is that you're not discarding high momentum modes, you're suppressing them. How do you do that? Consider the kinetic term, right? This is the kinetic term. We're going to put some function k minus 1 of minus del squared over m squared here, right? I'm modifying. What am I doing? And now this k has the following property that when s is small, this k is 1. When s is large, this k is 0. If this k is a sharp function like this, what you end up with is sharp momentum cutoff. Right? So you just pick a different function that's smooth and there vanishes. This way of viewing quantum field theory, it will make the path interval regulated. However, you have not discarded any momenta, any particular momentum. You just suppress the UV. How can you see this is suppressing the UV? Can anyone see that? Why is this suppressing the UV? So pick a momentum mode that's high, large, right? So del squared over m squared will give you a large value. So you have to look at k of s for s large. That means k of s is small. What is k minus 1 of s? Is huge. That huge number sits here. So what have you done? The weight function, the measure, now is, there's a huge number sitting in front of it, e2 minus a huge number. That's tiny. So you're suppressing the contribution of such field configurations that are large momentum heavy in the path interval. But you're not discarding any particular modes. This is smooth cutoff. Good. Now, of course, what this does in Fourier space is, well, okay, so I said this. What it does in Fourier space, oh, I have not, no, that's good. What it does in Fourier space is k minus 1 and minus p squared over m squared. What it does is what is the propagator for this theory? The propagator for this theory is the inverse of that thing. Right? So I didn't put the mass term. Good. So what is the propagator here? It would be capital lambda. Good. It's the inverse of that. Now, what is this function? This function, it suppresses the high momenta. This is the opposite of what you were writing yesterday, which was a polynomial. You're writing that because you knew you're going to have divergences. The coefficients of that polynomial, term by term, they were counter terms. You just didn't call them that. Those were the counter terms, right? Here, what you're doing, well, if you want to regulate, you would like a function that vanishes really, really fast at high momentum. Ideally, it vanishes actually double exponential, e2 minus p squared over m squared. In the original papers that Polchinski had, he took it to be double exponential, like e to the power of e to the power or something. Really a crazy suppression. You only suppress the kinetic term. If there's potential, you don't touch that. The potential is just adding, right? That potential, like this suffices. Because if the interaction term, well, what happens to Feynman there? There are a bunch of always external legs. Whatever process you have here, in here, there are Feynman diagrams, and there are loops and momenta propagating. The moment that momenta is very, very heavy, is just suppressed. As a matter of fact, to arbitrary ordering perturbation theory, you expect, as we were discussing this yesterday, you expect the structure of the divergences to be polynomial. So you would like this guy to be exponential to make sure that no matter how badly divergent and polynomially divergent it is going to kill it. It's not good enough if you want to have a non-perturbative regulator. A non-perturbative regulator, I think you use something even crazier, double exponential or something. Okay. All right, here's what the theory looks like. And the normalization equation is this mddm of z is 0, as before, right? But what you're doing now, so previously what you were doing, so here's our k function. right? K of S. This is K of S for sharp momentum cutoff. What is S? S is P squared over M squared, right? So as you change M, if I were plotting this as a function of P, for instance, this is getting shifted this way. And this function, the profile of it is just suppressing further and further these modes. Right? So, but it never discards the UV, it just suppresses. And it's more aligned with the idea that there are UV modes, but they just don't affect your physics. Yeah.
So as long as your K function is exponential, at least exponential, it should be independent of the specific function.
Very good. If you do a calculation and the final answer depends on the K function, it means it depends on your choice of regulator. That's bad, right? We're gonna that very good. That's very good. So when in principles of field theory in QFT1, I said that quantum field theory observables are low energy observables, and by definition they're independent of the UV, right? Whatever goes on in the UV doesn't matter, so I should be able to arbitrarily choose this guy, this function. Now we're gonna see that it's not always the case. As a matter of fact, things can depend on this, and that means scheme dependence, and that means that like I'll actually discuss that. All right, good. Now, what does this do for you? What's such a big deal? Like the sharp momentum cutoff is just like a particular case of this. You picked a smooth spot. What is interesting is that it turns out that using this is the part of the lecture that I'm not giving. In QFT1, we saw how to there were these non-perturbative equations for quantum field theory. They were called Schrödinger-Dyson. Using Schrödinger-Dyson equations, you could explicitly write down beta functions and equations for it. And interestingly, these results are completely, like, at least on the they're structurally non-perturbative, like completely structurally non-perturbative. And then here are the lessons that come out. So I'm not going to do that lecture, but these are the lessons I want to share with you guys. Under the RG flow, we've seen this before, but this formulation makes it very manifest that all sorts of non-local terms are generated. And if you're not close to an IR or UV fixed point, the action can and generically does include non-local terms. So the word close is important. What does it mean? How do you measure being close to a fixed point? The theory is non-perturbative, right? So what does it mean? So if you have some dimensionless parameters, for example, a bunch of marginal things, deformations, if those variables are now numbers, if those numbers are small, then you would say you're close to a fixed point. But what if those numbers are not small? If those numbers are not small, do you have any reason to write the local action? Right? In QFT1, I said principle of locality. It assumes that, I said that write down an action. Like this is Landau's principle. Order by order expansion of phi and, and derivative expansion. You immediately realize that every time you are writing a dimensionless coupling, you better put a small value. Because otherwise, there's not much sense of including an order 1 coefficient in front of a local term. There's generically all sorts of non-local terms. Non-locality or almost locality is a feature near a fixed point. But this is good in a sense, because this is the regime of validity of quantum field theory. Condensed matter theorists knew about this for a very long time. Quantum field theory captures the physics near the critical points. As far as we're concerned, the UV of Stano model could be a lattice model, right? I'm saying something crazy, right? But it is possible that there's a lattice model. The UV degrees of freedom are really, really, like fine-grained, some sort of crazy structure is there. And if you squint enough, there's a phase transition. There's a continuous phase transition. And then there's a fixed point, and deep in the infrared, there's an infrared fixed point. Deep in the infrared, we're getting standard model particle physics, right? And our physics is independent of that. Now, if the lattice structure, if you're not that far from the lattice structure, quantum, like condensed matter theorists have known for a very long time, you're not going to get a continuum theory. You're not, even if you try to get a continuum theory, there's no reason for locality. Locality, all of that is really near a fixed point, right? So it reminds you that even though in high energy physics, we are so accustomed to thinking in terms of locality and continuum limit or continuum theories, still you should be careful with this. Yeah. So those principles of Landau all assume in the sense that you're near a fixed point. Another thing that's very important is that this comes out of it, and I don't have time to explain it, is that away from the fixed point, couplings and beta functions become scheme dependent. Scheme dependence here means they depend on the choice of K. So physical observables shouldn't, right? So in non-perturbatively, beta functions are not observables. Couplings are not observables. And it gets a little bit tricky. Things get a little bit tricky. It's all okay at the end of the story, but you have to rethink a lot about what quantum field theory is at a non-perturbative level, right? So everything we've said, in a sense, in this course up to here is really strongly relying on perturbation theory. Or not, maybe not, I shouldn't say perturbation theory, but being in some sense that I haven't described near fixed point. I haven't described it clearly. Yeah.
That obliteration of locality happens because of the mathematical structure itself of the argue flow, or because there are physics that actually are involved in that non-locality?
Think no, you just do the calculations and you find that there will be non-local terms that appear. It has to do with the fact that, well, what is interesting is that these non-local terms, of course, they're going to be scheme dependent. They're going to be related to your K function that you picked. And then one of the lessons is that when you take the limit of the K function becoming a short momentum cutoff, in that limit, you're pushing a whole bunch of things under the rug, right? And that is, in a sense, why renormalized perturbation theory using counter terms is so successful. That's heavily relying on the fact that depends crucially on the fact that you pick a sharp momentum cutoff. If you try to do normalized perturbation theory, right, with a different cutoff, one of these smooth cutoffs, one of the things that you realize is that local counterterms might not be enough. As a matter of fact, you need counterterms with that have the same pattern of non-locality as your K function. This is very crucial. This is sort of the lesson that comes out, right? When we did renormalized perturbation theory, well, for two reasons things were good. One was that we only did one loop really. At one loop, no matter what you pick, everything is good. One loop is pretty simple. At higher loops, things get more complicated. Also, I was very careful working with dimreg or dimreg or sharp momentum cutoff, just to avoid anything else, right? But that is why people like AJ as a particle physicist, when you look at their tables, they quote some calculations and they say MS bar scheme, right? Because they know these are calculations not at one loop, they're at higher loop calculations, so they have to be very clear about what scheme they picked, right? That's a form of cutoff regulator, and a different choice of regulator, your answer might be different. Good. All right, so these are the key lessons. Yes.
So is the scheme dependent probably related to the
Yeah, of course, yeah. So they're all, well, I mean, depends what you mean by related. These are features that come out. None of them are like, for example, you could, by making a scheme, picking a scheme like sharp momentum cutoff, you might get the impression that the theory stays local counterterms are good, but that only gets you somewhere up to a point. Once you start doing higher order perturbation theory, even though you picked a very nice choice of K, you still see scheme dependence.
Yeah.
Now, if you picked a very non-local K, you see the non-locality in your face just right away.
Yeah, I mean.
So they're related, but in that sense.
Here you mentioned this case about the series away from the fixed point. But you also said that if we do the higher order perturbation theory, we will also see the scheme dependent. So we get the non-locality just higher order fraction?
No, so okay, very good. When you do perturbation theory, right? Every time you do perturbation theory, the kind of terms that you get are going to be hard derivative terms at the end. What is this hard derivative? Hard derivative term could be viewed as a non-locality, right? Think of a lattice. So you have a bunch of sides on the lattice. What is a local term? Phi of x. What is a derivative? It's phi of I. Derivative is phi of I plus 1 minus phi of I. Right? What is a two derivative? You have to do this minus phi of I plus 2 minus phi of I minus I plus 1. What's the third derivative? So there's local, there's one derivative, two sides, two derivatives this much, three derivatives, and so on and so forth. But in the continuum limit, all of these become like local. Now, if you had an infinite higher derivative terms, that thing, you can't just, when you take the continuum limit, you can't say that those infinity is smaller than my continuum limit. So, yeah.
Yeah, so we just do higher order fraction and it will cause the non-locality. So why would we consider the principle of locality as basic?
Because all we can really do at this level of this course is perturbative quantum field theory.
Yeah, but particularly you just do higher order, you will have
No. So when you do higher order with this, like in the standard model, right?
Yeah.
What you obtain is higher dimension operators. So in perturbation theory, to order 2, order 3, you get higher order terms like this, but they all look local. This is a little bit artifact of the choice of the scheme you've picked, which is a sharp momentum cutoff, but that's okay. That's okay, right? So we could do calculations, and it's all good up to that order. You shouldn't. Another thing that I've not explained at all is that Feynman perturbation theory is not a convergence series. So you shouldn't be calculating this to 102 loops. That's just junk. That's garbage. Most of these theories, these are almost all of them, they're asymptotic. So going to third, fourth loop, fifth loop, you get closer to the answer, and at some point you turn around and just go away. So your sums are just like horribly divergent. That's why non-perturbative quantum field theory is what it is, and how to formulate it is the main central question of foundational theoretical physics. Now, there's a lot we know about it, but I'm not covering that in this course.
Is like a house on the, like it has holes in the wall everywhere.
There are a whole bunch of things. So one thing that you already know about, one way of thinking about it, is the following. You know that if you, I've said this many times in the course, really the tool we have, the tool we have to walk away from, one of the ways to walk away from perturbation theory and do something non-perturbative is symmetries. If you have a lot of symmetries. Now, if you could invent a different approach to quantum field theory that are scale invariant, conformal field theory, if you could invent an approach to conformal field theory that doesn't rely on this, that way you would identify a bunch of fixed points. Now, around each such interacting fixed points, you could do perturbation theory. This is called conformal perturbation theory. Right? This has been a very successful program in 2 dimensions. In higher dimensions, there's been some success. But finding interacting CFDs is one way of going about this, doing this. Then the other way is supersymmetry, but we're not doing this. Symmetry is basically the principle. Or if you're in such low dimensions that integrability does something for you. Integrability is like whole different game. All right. All right, I have to start today's lecture. None of this is today's lecture. All right, so we're going to completely change gears. We're going to go back to classical field theory. We're going to talk about gauge redundancies. There will be 2 lectures, hopefully, not more, that belong to QFT1, and now I'm teaching this. What are we going to cover? We're going to say what gauge redundancies are, how are they related to locality, why are gauge theories sometimes incorrectly called local symmetries. This is old terminology. I absolutely suggest to avoid it, but I have to explain to you guys why this was old terminology. And what is the action of a non-abelian gauge theory, aka Yang-Mills. All right, so let's go back to electromagnetism. This is classical. Everything I say classical. We saw that in electromagnetism, I hope we saw this, the physical degrees of freedom were B and E, magnetic and electric field, that we packaged into F mu nu. This is field strength. So field strength is the physical degrees of freedom, has physical degrees of freedom. But there's no action, there's no local action you could write down for the field strength. So for that reason, to introduce a local action, we invented a gauge field that has some fiducial degrees of freedom. These are just like redundant, made up, right? They're completely made up, and they have to be discarded. And I want to insist that we did this because we wanted to insist on a local action. Okay? Now, why were we struggling to write a local action? This is the thing that I'll explain. Because these theories, gauge theories, electromagnetism included, are theories that have some genuine non-local degrees of freedom. Not every theory. So I started by saying that, like all theories, there are local degrees of freedom. These theories have non-local degrees of freedom. End of the story. And the way to see that is through the Aharonov-Bohm effect. Did we discuss this in QFT1? We did. Okay, but I'm going to discuss this again. Yeah, and this is intimately tied to the fact that we can't write down local action for using F mu nu, E and B for gauge theory. All right, so this is a philosophy. All right, so there are 2 options to describe these theories. One is using local fields E and B, and then you could try to talk about those and then talk about non-local operators. These are going to be Wilson loops. That's one way of describing it. You can't use the action principle, but you could still do a lot of calculations. You could work with the equations of motion. Classical field theory are just perfectly fine, well defined with equations of motion, right? Maxwell equations, you could write them down. It's all good. Everything on both sides of Maxwell equations are actually physical. Or you could work with the local vector potential, right? Now, working with the local vector potential in the quantum theory has the advantage that it will include the non-local operator Wilson loops. If you're careful with discarding the unphysical things you introduce, you do everything in one shot. You just path integrate over mu over the vector potential, and just discard systematically the redundancies you introduce, you're good. You mod out by the redundancies you introduce. However, again, because there's no local action you can write down for these, it's going to be hard to quantize that theory directly. In this case, actually, we're in the U1 case, gauge theory U1, we're in a lucky situation that F mu nu is gauge invariant, is a physical observable. We're going to see that for non-local part, for non-abelian groups, F mu nu is not even gauge invariant. All right, so let me just say this, that old terminology, local symmetry, gauge symmetry. Modern terminology, local symmetry is called higher form symmetry. So these theories, they have symmetries They're not local. They're called higher form symmetries. So this is a modern terminology for it. It's not a gauge symmetry, it's a gauge invariance. All right. Similar, so here, this I'd explained before. Every time we had global symmetries that were given by some continuous symmetries and some, Noether theorem. The first Noether theorem told us that there will be conserved charges. In gauge theory, what happens is that the gauge invariance, right? The gauge principle of gauge invariance, we reformulate, or in terms of some fiducial symmetry, right? That local symmetry, and that will give you some conservation laws that are called ward identities, right? These are not conservation laws. These are equations that must hold to make sure that you have killed all the unphysical degrees of freedom. All right. Why introduce gauge redundancies? I'm gonna repeat this. I think I had this slide in QFT1. Maybe I didn't. I don't remember. So I'm gonna motivate it. First, we see a massless spin 1 particle in nature called photon. We did representation theory of massless spin 1, and we saw that it has 2 polarization, right? And there's no degree of freedom in the direction of the propagation. You would struggle to write down a local action for such a vector field. This is a first thing. Now, if you write down a spin 1 action, the action for spin 1 particle, right, which is going to be a vector, it ends up with 3 degrees of freedom, and you need a gauge invariance to kill the longitudinal moment, right? Similarly, there are other massless particles we've seen in nature. Graviton. So graviton is spin 2 particle, and similarly, we can't write down a local action for it, and the challenge for it is you can't write down a local action. So what you do is you introduce a extra fiducial gauge degrees of freedom, and the issue is to the massless spin 2 particle graviton has only 2 degrees of freedom in 4 dimensions, whereas the spin 2 has too many, so you have to kill them. There would be analogs of ward identities for gravity, right? To make sure that you kill them. Remember that again. There's nothing wrong with gravity as a quantum theory if you're doing EFT, perturbation theory, up to a certain loop. Okay. The physics of, but these are 2 things. Here we're just insisting on locality because we want to write down an action, because path integrals were convenient, right? But the real reason is that electromagnetic fields are not just E and B, are not just F mu nu. They have gauge theories, have genuinely non-local degrees of freedom. They are called Wilson loops, and they appear only when quote unquote topology is non-trivial. So I don't think I'll have time to describe higher form symmetries in their full glory, but if you have a theory, so a loop, right? A loop is a one-dimensional non-local operator. Well, so we're going to introduce we're going to associate a non-local operator to a loop, right? Which cannot be generated if you split the loop into parts. There won't exist operators here, here, and here that you could just combine to generate the whole thing, right? These are genuinely non-local operators. If you have one-dimensional objects like this, it's a one-form symmetry. If you have p-dimensional surface operators that are non-local operators, these are p-form symmetries. And if you're curious what a zero-form symmetry is, it's global charge. Anyway, that's just for you guys. But we're going to talk about only the one-form symmetry. That's the modern terminology, right? So gauge theories do have a symmetry. It's called one-form symmetry. It's topological in a sense. Yeah. Now, why is gauge invariance called local symmetry? This is, I said this, I repeat, it's old and imprecise language. Symmetries leave the action invariant. Redundancies leave the action invariant too. But there's a difference. Redundancies are made up, right? But these are actual transformations in the Hilbert space. So when you do have a symmetry, when you do a symmetry transformation, you know, there's a unitary that acts in the Hilbert space, right? A vector goes to another vector. That unitary leaves your vacuum invariant, hopefully, if it's not spontaneously broken. Your fields transform covariantly under the action of this unitary. You know, you see the adjoint action of the unitary, the fields transform covariantly. In gauge invariance, you could do a field transform, gauge transformation, but there is no operator in the Hilbert space. This is just all made up, right? It just means that your phi was not physical to start with. You have to mod out by such transformations. Often the way we do it is that we assume the field A mu or these are physical. We construct a larger Hilbert space. Now in this Hilbert space, we're imagining some physical transformations that are gauge transformation, and we look at the invariant sector. We say once we construct that Hilbert space, all physical states are going to be the states that are invariant under the action of these transformations. That's why historically this has been called a symmetry. But notice that in the physical states, in physical vectors in the Hilbert space, there is no such transformations as gauge transformation. All right. Okay. I'm tempted to explain this a little bit more, but anyway, maybe I'll do that later. All right. So symmetries. In global symmetries, what you do is, for example, you have some sort of, you could have space-time or internal symmetries, right? You're under these, your field transform this way or this way, right? And if you have fields with spin, they transform this way, right? For gauge theory, under gauge transformation, you could write all of these relations, but you have to be aware that these are completely unphysical, right? These are all made up because you insist on a local description. Yeah.
Do we have to change our definition of symmetry at all to accommodate for higher form symmetries, or?
Well, it depends what you mean by symmetry. What is your definition of symmetry?
Something that means the Hamiltonian.
Yeah, you have to do a little bit better than that. Yeah. Yeah, it's actually an interesting. So that's why we talk about generalized symmetry. Yeah. So that sometimes we hear generalized symmetry because of this. So in a sense, that the terminology is that gauge theories have generalized symmetries. These are higher form symmetries. Maybe I'll explain that at the end of the class. I don't think I'm going to make it very far today, but anyway. Now, what is the word local? When people say local symmetry, what is that? It has a beautiful origin. So now I'm going to explain this in a funny way. Let me explain in words. Gauge theories have non-local properties. Meaning what? Meaning that if you had a local theory, right? You made a change here, you changed something here. That change will have to propagate, will have to make a way, propagate with the speed of light and get somewhere and do something, right? For instance, if I have a theory with actual global symmetry or something, I apply some sort of a unitary transformation here. That's physical unitary transformation, right? That will do something and then that will propagate with speed of light and will affect something somewhere. You got that? All right. In global symmetry, you take your field phi of x and you say apply a unitary at every point in space-time, right? You take the spins and all of them, you flip them. Now, imagine, so why is that a symmetry? Because, well, there's u dagger, the kinetic term is invariant. That's pretty obvious, right? Now, for a second, imagine you had a symmetry that could depend on the rotation, the amount of transformation you're making could depend on the position in space, right? If you introduce such a thing, well, then del mu of phi prime will be this. Now del mu acts on u of x, so it would no longer be invariant. The kinetic term will no longer be invariant, right? But if this transformation is all made up in my head, things will have to be invariant. We'll see that. Okay, everybody's with me? So for a second, good. All right. Now, in electrodynamics, in U1 gauge theory, the U1 has to do with U of x being just a phase, e to the power of I alpha of x, x at every point. This means what? It means that if you have a matter field, right? You're describing with some field phi. You apply e to the power of I alpha of x to it at different points, right? And this is a symmetry. So, like symmetry, right? Like, because it's a redundancy of description. That's unphysical. That whole degree of freedom is completely unphysical. If this were actually doing something, if you were doing something to this, it would have to propagate with the speed of light, right? You couldn't have this be simultaneously independent of what your transformations are. All right, so you have a field phi. You take a derivative of it, and this is how under this transformation, it transforms. If you want to force this to be invariant, you have to change your notion of derivative. How do you change your notion of derivative? You define what's called the covariant derivative. Covariant derivative is del mu of phi of x minus a bunch of things, i.e. a mu of x phi of x. All right, I introduced this guy. This is an auxiliary made-up field I introduced. The goal of this field is to make sure it cancels these terms. So if I now transform covariant derivative, this is how it transforms. Now, if a mu transforms exactly like this, it will cancel this term, right? So, good. And then I call a mu. So this a mu has to be a Lorentz vector, as you can see. So because it's canceling del mu of alpha. And it's associated with the spin one. We would associate this with spin one particle. This is what the gauge field is. So the universe, when we're talking about the photons, what it is that there are a bunch of charged particles, right? These charged particles, when we describe them, we're using too many degrees of freedom. If you take these degrees of freedom and apply e to the power of I alpha x at each point, that is not, you're not doing anything, right? And to make sure, so that should be thrown out of the physical description of the theory. To make sure that's the case, invent a field. Every time you do, there's another field that lives in the universe that every time you apply this, that field changes exactly with the right amount so to cancel this, right? So that is what gauge field is. All right, so now, if phi, this is your charged particle, right, is a complex field in some fundamental representation of UN. What we just described was a U1 representation of U1, right? It's one-dimensional. Covariant derivative would be del mu of identity, right? These are n by n unitary matrices minus ig a mu of x. which is now matrix valued. So at every point in space, your gauge field is going to be matrix valued. If your fundamental is n dimensional, it's an n by n matrix. Good. All right. So here's a covariant derivative. How does it transform? For the transformations to cancel properly, right? For a UN transformation to be a symmetry, you have to apply that and make sure that a mu as a matrix transforms properly. How should it transform? It should transform in the following way. A mu should be fundamental on the left, anti-fundamental on the right. That's called the adjoint, right? Fundamental left and anti-fundamental on the right, plus I over G U of X del mu of U minus. Do that here. So A mu of X transforms in the adjoint representation. If you have charged particles in the fundamental representation, then your corresponding gauge field transform in the adjoint. Right? If your fundamental field in some representation R, the gauge field is transforming as representation R on the left, the other one on the right, the anti one on the right. All right. So can I have like 5 minutes? Let's see, how far can I get with 5 minutes? I'll stop after two slides. Okay. In the case of SU2, so imagine SU2 gauge theory. This is going to be actually a theory that's relevant for nature. The Lie algebra, if you have SU2 matter field and fundamental representation, right? What's the dimensionality of that? Two-dimensional complex, right? What are the representation of your gauge fields? It will be the 2 by 2 complex matrices, and it's actually nothing but Pauli matrices times half, right? So here's where your gauge SU2 gauge field looks like, right? I'm just writing the Paulis, expanding the Paulis, right? This is I'm not calling it Z because Z sounds like space-time. A mu index is here. Space-time index is here. These are 3, 2, 1. These are representation dimensions, right? But more generally, if A is some label for your fundamental, your gauge field is going to be a matrix in that. So it has A and B of that, right? Now you could pick a basis for whatever representation you're working with. These are matrices, and these would be the coefficients of them. And yeah, so we've seen this before, right? So you can expand the matrices, the fields, all of that this way. I'm not going to remind you this. This is just the adjoint, right? In the adjoint representation, what are the matrices you pick? FABCs, right? Those become your matrices.
When you say adjoint representation, you're treating the endomorphisms of the group itself.
Endomorphisms of the group. No, the adjoint representation. Adjoint representation means the following. Means that so you need what is a fundamental representation? Well, you remember that. So you use FABC. This, well, I think maybe I want to do. How do I want to do this? I forget. Something like this. I think I'm putting the labels in the wrong place, right? Because remember, the goal is you want a bunch of matrices to satisfy the commutation relation of the Lie algebra. We showed that these guys do. So you could pick them as the matrices. This is the adjoint representation. And it's actually equivalent to a fundamental on the left and anti-fundamental on the right. All right. I'm really behind. It's okay. I'll remember slide 23. Okay. So, to write down a gauge invariant action for scalar field, charged scalar field, that's in representation R of a gauge group, what would you write? Well, you write the kinetic term this way. right? How about this? Is this okay? That term is okay, right? Because the issue was coming. This has u of x, this has u of x dagger, they cancel out. The issue was the derivative. Every time you have a derivative term, all you need to do is you take your old action, you replace your derivatives with covariant derivatives. Right? That's what you do. All right. So in a homework, you'll see that when you apply Noether's theorem, in the case of global charge, we found that the charges we found were integrals of the current on integrals on the are objects on the codimension 1, right? So you integrate the J0 on 3 manifold constant time slice and that gives you a charge. In the case of gauge theory, you integrate over a codimension 2 thing to get a charge. Electric charge. What is electric charge? When they were teaching you electric charge, they didn't talk about time. They said put the charge here. You integrate to find the charge. You integrate the electric field on a sphere. That's a 2-dimensional object in 4 dimensions, right? That has to do with p-form symmetry. Global charge is a 0-form symmetry. So the charges are codimension 1 objects. 1-form symmetry is gauge theory. The charges are codimension 2 and so on and so forth. There's a beautiful topological story for this. This is our modern understanding of it. Okay, I'll have to stop at the beginning of the field strength. But are there any questions? You'll work this out in a homework problem.
Eventually, when people saw that they needed to include these kinds of symmetries in the standard model, it's because experiments told them to, or it was just
Electromagnetism. Electromagnetism. Forget about Sanimal. Electromagnetism is a U1 gauge theory, right? And there was people discovered a long time ago that the photon has 2 polarization. And if you try to write down, Maxwell equations were known for a very long time, but people struggled to write down a local action for it. And people realized that if you vector potential is what is called in electromagnetism, right? The Carroll and all of that. These are all manifestations of just a 1-form symmetry. The modern understanding of things became more interesting in a sense when people realized that so we saw that gauge theory, U1 gauge theory is a free theory. Is that clear? Photons don't self-interact, right? Non-abelian gauge theory is an interacting theory, so it could exist as an interesting theory without charge matter, without quarks. Charge matter would be quarks or something like that. Right? So that theory is called Yang-Mills. We're going to discuss that. It's an interacting theory, if it exists. At least it's a classical interacting theory. And there was the calculation of beta function of Yang-Mills that played a crucial role, and people discovered that it does give you examples of interacting theories in 3+1 dimensions. That's the whole point. Right? That's why the detour. Yeah.
So you say that the Noether's theory also works for the